So now I have a table in the graph for you to show you. Okay, so for our linear system with constant coefficients of second order, you can observe or identify the type of stability. So if P is negative, Q is greater than 0, means that we have two eigenvalues, real eigenvalues, which are negative. So when they are negative, then they will go to 0, right? Because the exponential function number 1t, number t. Because when number 1 and number 2 are negative, these two exponential functions will go to 0 as t goes to infinity. So that's why the point goes to the origin. Okay. So it is very obvious that if P is less than 0, Q is greater than 0, then the critical point P0 is stable and attractive. And it is stable only, not stable, not attractive when P is equal to 0. Okay, when P is equal to 0, but Q is greater than 0. Okay? In this case, you have a pure imaginary. So in this case, so you know that you have something like IAT, IBT, something like that. So you have a cosine and sine. So actually you have a circular trajectory. So that's why you have stable situation. And the other situations are all unstable. So let me write down with P and Q plane, all right? This is not a phase plane. This is about P and Q. And so we have okay, up to a circle, and we don't know. Okay, and we have quadratic functions. Describe so we have delta, which is equal to P squared minus 4Q. This is our discriminant. Right? So discriminant is a function of P and Q, and this is equal to 0. All right, so the curve corresponding to the discriminant equal to 0. Okay? So this part, so we have here, this is corresponding to centers. All right, so this compare with the previous table. Okay, here P is equal to 0, so this is corresponding to the centers. So this is corresponding to center. And for here you have this is less than 0, okay? And for here this is greater than 0. So the discriminant, okay? So now I can say that this is node. You have node here. You have node here. Okay. And for here, downside here, you have spiral point. Okay. Oh, saddle point, sorry. You have saddle point. Around here, and this region, you have spiral point. You have spiral point. Okay? And the node here, they are all improper node. Okay? And here you have proper node. Now, the region of stable and attractive actually is here. The second quadrant. Okay, so in here you are stable and attractive. Okay, so in the second quadrant, this is second quadrant, and stable. Excluding the q-axis here, because on the q-axis correspond to centers, so they are all only stable only. Okay, so only the second quadrant without the coordinate, okay, corresponding to stable and attractive region. Okay, so now I have enough time, so for 4.5 is for self-reading. Okay, 4.5 is important for dynamical systems, especially for nonlinear systems. So 4.5 talking about how to analyze a nonlinear system by linear system. Unfortunately, I don't have enough time, so you have to read by yourself. Now, I would like to talk about how to solve non-homogeneous linear systems. Okay, so we will consider so we will consider non-homogeneous linear system. Okay, so we consider non-homogeneous linear systems. In general, the coefficient matrix A may be functions of X. Okay. But most often we will consider A to be constant matrix. Okay, because we know how to solve this type of linear systems with correspond. And the G is the non-homogeneous part. Okay, and of course in general it's a vector function of X. Okay. right? Now, a general solution of 4.6.1 exists, okay? And as we know, such a general solution includes all solutions of 4.1, okay? By a theorem in section 4.3. Okay. And such a general solution can be written in the following way, okay, where is a general solution of the corresponding homogeneous linear system. Okay, and yp is a particular solution of the non-homogeneous linear system. Okay? Again, we have two general methods. One is called the method of undetermining the coefficients. The other one is called the method of variation of parameters created by Lagrange. Okay. So let me take two examples to illustrate both methods. Okay, so we will use them. I will just demonstrate the multiplication rule. Okay, so we consider a linear system y prime equal to ay plus g, okay, which is equal to the coefficient matrix is a constant matrix, all right? And the non-homogeneous part, okay, g is this vector function. Okay. All right, and the eigenvalue of A are 2 and 4. Okay. So you can solve the eigenequations. Okay, I just skip this step. Okay. So you have to go to solve it. Actually, the eigenequation is, as you can see that, all right, maybe I can say things. Determinant A minus lambda I. This is equal to lambda square 8. Okay. Okay. You have to solve it. Okay. So the eigenvalues are, I'm sorry. Sorry. sorry, this one. So this minus 2. I'm sorry. Minus 2 and minus 4. Yeah. Sorry. So it's minus 2 and minus 4 because here is plus 6 times. Alright, and so a general solution for the homogeneous linear system, that's YH is C1. Okay, and I have to find the eigenvectors, right? And also find 1 and 1 minus 1 are eigenvectors, okay, of A corresponding to eigenvalues minus 2 and minus 4. Minus 4 respectively. Last. So of course you have to solve the eigenequations. You have to solve 2 eigenequations, one for each eigenvalue. Just skip the steps. And so that YH is equal to C1, 1 e to the t plus C2, 1 minus 1 e to the minus 4t. Right? So this is a general solution of the corresponding homogeneous linear system. And note that minus 2 in G. We know G is minus 6 to function. In here, it's an eigenvalue. Okay, so you have to know that the non-homogeneous term is an exponential function with the parameter minus 2. And this minus 2 is an eigenvalue. Okay, so you can see e to minus 2 will have effect because this is a solution for a homogeneous system. So we have to be very careful to find a particular solution to YP. So by our previous experience, we will try the particular solution to be something P plus U. Okay, so we will try, right? The particular solution to be a sum of a vector times t times e to the minus 2t, okay, plus u times e to the minus 2t. Okay, so this is the candidate for us to find a particular solution. So now, the derivative of the particular solutions becomes to, okay, this is 3 e minus 2t minus 2v t e minus 2t. Okay, and for here this is minus 2 u e minus 2t. Okay, so this is what comes. Okay, but this is equal to A by P plus G, okay? And the AYP is A with P, E minus P, G plus A U plus G. G here. Okay, so now we have this expression is equal to this expression. So we compare for the function t times minus 2 e to minus 2 times t. We know that A, 3 is equal to minus 2, 3. For the function e to the minus t, we have A, U equal to, okay, I have to write down, this is equal to minus 6, 2, and equal to 2. So we have U plus is equal to here. So it's equal to minus 2U. This is an eigenequation, and we have solved this one. So we know that V is equal to alpha 1. Is alpha not equal to 0. Okay, so we know V is any eigenvector corresponding to eigenvalue number 2. We already solved it. Okay. So now we have to solve for the second matrix equation here. The second matrix equation. So actually, so this is going to A plus 2I U equal to V minus 2. Okay. Okay. And so that so you can see that we have U1 and U2, and we have alpha minus 6 plus 6 alpha minus 2. Which V is alpha here. Okay. And for here, A is equal to minus 3, so we have minus 1 and 1, 1 minus 1. Okay. Now we add the first row to the second row. So we have minus 1, 1, 0, 0, U1, U2, alpha plus 6, and here, so this is 2 alpha plus 4. Now, this non-homogeneous system of linear equations to have a solution, so we need 2 alpha plus 4 equal to 0. Otherwise, there is no solution, right? So this is implies that alpha should be equal to minus 2. So the eigenvector we have to use is 1. It's not 1, 1. Will be minus 2, minus 2. It's crucial, right? To use alpha as a parameter because we are facing with non-homogeneous system of linear equations. Okay? So it's possible to have no solution. But we won't have a solution because we know we should have a solution. So we try our best. And so we have to introduce this parameter alpha. Okay? And we get the alpha is equal to minus 2. So once alpha is determined, so we know, so that we are able to solve the equation. So now alpha is equal to minus 2. So this one becomes 2. So we go here, this is 0, and this becomes 4. Okay? So that we can solve. So we know that U2, U minus U1 plus U2 is equal to 4. Okay? So this is implied as U2 is equal to U1 plus 4. Okay? Right? So this implies as U vector is equal to K and K plus 4. So this is K 1 1 plus 0. Okay? Right? So we refine solutions. Alright, so a general solution of so is y equal to y h plus y t. So this is down to c1 1 1 minus 2t plus c2 1 minus 1 minus 4t minus 2 1 1 t e plus 2t. Okay, because the v we have is corresponding to alpha equal to minus 2. So this is v used and plus 4 minus 2t. Okay. And now we'll see where is the k come from. Well, surely can let k equal to 0, right? So we will select k. You may say, well, you may say we can use other k. That's fine. Consider actually k into here. If you put k here, you can combine this part with this one, right? Actually, it's included in the first one already. So nothing new. Okay, so we solved our problem. Okay, so this is basically the idea of the method of undetermined coefficients. All right, so the next one is the method of variation of parameters okay, so we take the same example as in above. Okay, so we take the same example as above. Okay, but now we use the method of variation of parameter. So now we have a pH, okay, already for C1 1 1 plus okay, so we have a 1H, a general solution. Okay, so it's a general solution of the homogeneous linear system. All right. Now, the variation parameter is something that we will change the constant CCLu to become functions of it, right? The function of t, function of t. This is the idea of method of variation. But we will, so before that, we will rewrite yh as the following form. Okay, so we will remember we used this form before. So we use the fundamental matrix. So this is T. Okay. So we write this linear combination as a matrix, the multiplication of two matrices. Okay, and so this is called Y, T, and C. Okay. Alright, so yeah. Because the notation is more complex. So this is our from the mental matrix. We call this matrix the fundamental matrix. And now we try yp equal to our fundamental matrix times ut. Okay? Right. So the coefficients, this is the arbitrary coefficient vector, so it's a constant vector. We replace the constant vector by a vector function. Alright, so yp from the first derivative is equal to y prime t ut plus yt u prime t. Right? And this is equal to a yp plus g, right? AYP, because the yp is a particular solution of non-homogeneous linear systems. Okay, and this is a, and the y, p, ut plus but we know y from t, which is equal to y1 h1 h2 okay, is equal to a yh1 a because this is the from our homogeneous, we have two independent solutions for our homogeneous linear systems. Okay, and each one is a solution of the homogeneous linear systems. Okay, so this one is equal to this one is equal to this one, And about matrix manipulation, this is Y. P. You know that this is just our, so this is our H1. This is equal to our H2. Okay? We have two solutions. H1, H2. So basically, this is equal to our YH1. This is equal to our YH2. So we will just put YH1 and YH2 to form a matrix. Okay. So just put that down like this one. And then I apply the matrix multiplication. So you can factor out the matrix A, okay? Just using the matrix multiplication rule. And it is very simple for linear algebra if you know how to manipulate the matrix. All right. So this is what you have A and the YP. Okay. So you know Y prime P actually is equal to A times YP. Okay. So you can see that. You can cancel them. You can cancel them. So finally, so you get YP U prime P is equal to all GP. Okay. So you get a matrix equation. And remember, Y H1 and the Y H2 are linearly independent, so that their Wronskian W Y1H Y2H YH1 YH2, which is the determinant of the matrix. So this is equal to the determinant of the Y, the fundamental matrix. So Wronskian indeed is just the determinant of the fundamental matrix. Okay? And we know this is not identical with 0. This is not 0. Okay? Not 0. Never 0. Because H1 and YH2 are nearly independent. So we know the Wronskian is never 0. So never 0, so for every t, this is an invertible matrix. Right? The invertible matrix. So U prime P is equal to the inverse matrix times G. Okay? Then you always get the solution. Inverse matrix. Okay? And so apply to our theorem. So you have now and what is the inverse? The inverse is the determinant of YP, right? And the matrix. Because our fundamental matrix is 2 by 2. So the inverse matrix of a 2 by 2 matrix has a very simple formula. You know what is that? If A is A, B, C, D, what is the A inverse? Is the determinant of A and what? Do you know that? It's century, right? Now, you change the time and then, is that correct? You should know this from high school, right? From high school. Right, okay, so I just apply this formula here, and we already know the matrix like this one. So I have minus E, I have 2, 3. Okay. So this is the inverse matrix. And we are happy because the determinant never 0. Because our theorem tells us that Wronskian is never 0 for independent columns. Alright, so we have the theory to back up us. So of course we have this results. Okay. And so that's the U prime T becomes 2. Okay. So you will find that, and the determinant is minus 2. So actually, yeah, you can compute the determinant. The determinant actually is minus 2e, which is not easy. So I just write down. This is the determinant. Okay. So here we have e here. And okay, so you put it there. So you find that the solution is 1 up is 2 minus 4 to p. Okay, so you have integrating both sides. We have the UP, so we integrate both sides. The UP. Oh, minus 2, I'm sorry. Is that correct? Yeah, so it's minus 2, I'm sorry. This is a minus 2. Okay, so it's minus 2. And so okay. So this is equal to minus 2t minus 2 minus 2 e to the t. Okay. So we find the u, okay, and so phi p is equal to phi p and ut, right? So you do the actually you have constant, but we just need only one solution. So this is equal to okay. All right. So finally, you have minus 2 and 1 plus so maybe I write this way. Okay. Okay. So this is the particular solution. So a general solution is E1 plus C2 minus 1 minus 2 1 plus, but remember what is this? You can write it down to be minus 2 plus, okay, and this can be solved absorbed into here, right? Okay. So the only difference is here, but you can absorb this term into the first term. So you will see that the final result is the same as the previous one. And put it down. The other way is that I mentioned before, we can solve a system of linear equations by Kramer theorem. So I just mentioned to you that. Okay, so that is for today. I'm sorry to take more of your time. So we